Yes, a conductor may comprise one or two of the following components. Okay, I'll mention them. The RLC. The RLC. Okay, we have R for resistor. We have L for inductor, and then we have the capacitor. Okay. Now, of course, you know that a resistor is any device that opposes the flow of current, okay, and it also produces heat energy. Then the second one is the inductor. The inductor is any device, okay, when electric current is passed through it, okay, stores magnetic energy. It mainly stores magnetic energy. Okay, it stores magnetic energy. Okay, now the capacitor, on the other hand, which is the main topic for today, is that device that stores electric energy or charges. A capacitor is that device that stores electric energy or charges. Okay, now that we have the understanding of what a capacitor is, it usually comprises of two conductors, that's two conductive plates with insulator in between. So what I'm trying to say is that a conductor comprises of three layers. If I'm to draw this, it looks like this. This is what a capacitor looks like. It has three layers. Okay, three layers. Can you see what I'm doing? Okay. Please, I'm trying as much as I can to make it look like a 3D. So this first layer is a conductive plate. This first one. The last layer is another conductive plate. Then in between, this middle, this one is an insulator, okay, or a dielectric. Okay, a dielectric is simply an insulating material. Okay, what does that mean? It's a material that has a very poor conductor. Is a very poor conductor of electric current. So dielectric materials are materials that are usually insulators or are very poor conductors of electric current. Examples of dielectric, we have we have CAPGO. I use this acronym, CAPGO. Okay, C for ceramic, A for air. This is ceramic, is an example of dielectric. Then we have air. Then we have P for plastic. Okay, then we have G for glass, and then we have O for oxide of metals. Okay, so all of this CAPGO is the acronym for examples of dielectric. Now, to make the capacitor to have to comprise of what, two equal and opposite charges, it is connected to an external terminal. Okay, it's connected to an external terminal, which is what, battery. Okay, so if it is connected to a terminal, the diagram will look this way. It's going to be this. So we have this. Let's say this is the conductive plate. This is another conductive plate. Okay, across a terminal, the battery, so that it can have a positive and negative charge. Okay, now we know that this is the dielectric in between the two conductive plates. Now this one, now since of course you know that the shorter part of a battery is what, the negative, this one will be what, Q negative. This plate will now be carrying what, the positive charge. Okay, now what you have in between is the dielectric. Is that okay? Now the symbol for capacitor, okay, is this. Two equal lines. It has to be equal. Okay, this is the symbol for what, capacitor. The symbol for capacitor is not the same as that of a battery. Okay, now let's talk about Now, mathematically, I just want you to know this. Mathematically, not mathematically, experimentally, it has been proven that the magnitude of charge is directly proportional to the potential difference V. Okay, so we have this. Experimentally, it has been proven. Okay, and you know in mathematics, if I'm to remove the sign of proportionality, we introduce a constant. So we have Q is equal to what? CV. Where C is a constant, we have Q to be the charge, then we have V to be what? The potential difference. Is that okay? Now C, this constant is termed capacitance. Capacitance C. Now, what is a capacitance? Before I define what capacitance is, let's make C the subject of the formula to make the definition easier. So we have Q is equal to, from here, to make C the subject of the formula, we divide both sides by V, we divide both sides by V, and then we have C is equal to what? Q over V. Okay, if you divide here by V, V will cancel V. We are left with C, then Q over V. Now we can define what a capacitance is. A capacitance is what? The ratio of what? The charge between on either of the plate. The what? The ratio of the charge on either of the plate to the potential difference between the plates. Are you following? The potential difference between the plate. So it means if you are able to bring this out, you should be able to define what a capacitance is. I mean, that's one of the reasons I love physics. So now we have this as our definition. Now let's quickly talk about the unit of a capacitor. What is the unit? The unit is farad. The capacitance is measured in farad, F. So we have smaller units like the microfarad. We have what we call the microfarad. We have what we call the picofarad. We have what we call the nanofarad. Okay, these are the smaller versions of it. So the microfarad is equivalent to 10 minus 6 farad. Are you seeing what I'm doing? Then the picofarad is equivalent to I think nano is 10 raised to power minus nano from 9. Nano stands for 9. This, and then the pico is 10 raised to power minus 12 farad. I think this should come down so that you won't get it twisted. Picofarad is equal to 10 raised to power minus 12 farad. So it makes you to be able to switch in between to suit whatever you arrive at your final answer. So it means this is equal to 1 times 10 raised to power minus 6 farad. This is also equivalent to 1 times 10 raised to power minus 9 farad. This is also equivalent to 1 times 10 raised to power minus 12 farad. Okay. If I'm to remove this 10 raised to power minus 6, you can put this symbol. If I'm to remove this 10 raised to power minus 9, I hope you are seeing what I'm doing. You can put N. If I'm to remove this 10 raised to power minus 12, you can put what? P. So it means this 1P is the same thing as 10 raised to power minus 12. Now let's quickly talk about capacitance in series and capacitance in parallel. Capacitance in series. Capacitance in series. I want to beat time, but I don't think it will work. Let me just stop here. In the next video, we'll talk about capacitance in series and capacitance in parallel. I'm still Bukola Joseph, the physics enthusiast. Bye.